Within this video, we're looking at topics involving liquids and intermolecular forces. In particular, we're going to look at a few select properties of liquids, including viscosity, surface tension, and capillary action. We've seen that the diatomic molecules chlorine, bromine, and iodine at room temperature and pressure display different states of matter: a gas, a liquid, and a crystalline solid. Take a second. What intermolecular force explains these different states of matter for chlorine, bromine, and iodine? Explain your reasoning. The more you can describe that particular intermolecular force, the better. We also saw how a gas, a liquid, a solid had different characteristic properties. In this video, we're looking more closely at liquids. Here's a description of different properties involving liquids. How a liquid assumes the shape of the container it occupies. It does not expand to fill the container. It's virtually incompressible. It flows readily, and diffusion will take place. Within those properties, are any of them related to gravity? Oftentimes as a chemist, we're not interested in the force of gravity, but macroscopically, once the particles begin to fit together, gravity may become important. Do you make sense of any of those properties of a liquid in which gravity may be involved? The idea of diffusion. Here's a demonstration describing diffusion of food coloring in water. This particular experiment is looking at food coloring added to cold, warm, and hot water. And it's considering the rate of diffusion in each of those. It appeared that the diffusion was affected by the temperature. The diffusion or spreading out of the food coloring seemed to be faster in the hot water than in the cold. If you're not sure, double back to that part of the video. Why do you think diffusion would be affected by temperature? In terms of intermolecular forces, dispersion forces, dipole-dipole interactions, hydrogen bonding, ion dipole interactions, we want to know about all of those. We've been discussing water as a liquid. Water would include dispersion, dipole-dipole, and hydrogen bonding. It's not unusual to have more than one intermolecular interaction present. In fact, only when dispersion forces are present as the only force would you have a single intermolecular interaction present. With water, we end up having three. The way that we identify the ones that are present, we need to begin by able to draw the Lewis structure. From the Lewis structure, determine the VSEPR predicted geometry. Look at the VSEPR predicted geometry and consider whether we have a polar molecule or not. And also look at the connectivity to see if we have hydrogen bonded to nitrogen, oxygen, or fluorine. Melting point and boiling point are properties that are relevant for a liquid. They describe the temperature in which we will form the liquid and the temperature at which the liquid would become a gas. What are other properties relevant for a liquid? Viscosity is one property. Viscosity is the resistance to flow. Something with a high viscosity, like honey, does not flow very readily. Increasing the temperature of honey would change the viscosity. It reduces the viscosity and makes it flow more easily. Here are a few different hydrocarbons. Notice how the chains are getting longer and longer. And it turns out the viscosity increases as well. Here are the actual data for them, and it's definitely a pattern. The viscosity is getting bigger as those chains are getting longer. Why do you think the viscosity increases for these molecules? I see two different factors. One, I think the dispersion forces are growing larger as the molecules themselves are getting bigger. I can also envision how these molecules, as they get longer and longer chains, could get tangled up. It's like cooked spaghetti. As they get tangled up, that would be another factor that's leading to resistance to flow. Another property for liquids is surface tension. Here's a description of what's taking place at the particle level and what one might observe, where we have the insect hovering or even standing on top of this water. It's as if there's a coating on the top of the water, even though it's a liquid. What's happened? Well, if we look at the particle level, if there's attractions between the different molecules, a particle on the interior of the solution is attracted to all its neighbors. It's surrounded by other molecules in which there's an attraction. One on the surface, it's attracted to all of the neighbors, but notice there is no neighboring particle above it. This idea that there's almost a directionality and a pulling together creates the surface tension. Here's a water droplet. Due to the surface tension, it seems to begin to ball up. Something with an even larger surface tension would be liquid mercury. It has a very high surface tension, and if you pour it onto a surface, it definitely adopts the shape of a sphere, although it's a little bit flattened out there due to gravity. Let me show you a couple videos pertaining to surface tension. Food coloring is being added to the water droplet. Here's one more. As you watch this, see if you can consider, how is this behavior different when the water is at the space station, and why would it be different?
Hi, this is Scott Kelly aboard the International Space Station. I wanted to do a little demonstration of these paddles. They're called hydrophobic paddles, and they repel water, kind of like a raincoat. But up here on the space station, they allow you to play ping pong with a ball of water, and it's pretty cool. Neat stuff.
So what do you think's going on? One more property is capillary action. Here we see mercury in a test tube. At the particle level, it's showing how the mercury particles are attracted to each other, and they're describing that as a cohesive force, mercury being attracted to other mercury particles. Notice due to the surface tension, it's balling together. There's not an attraction that's of the same magnitude between the mercury and the glass wall. They would call that an adhesive force between the mercury and the surface of the glass. So because the cohesive forces are greater than the adhesive ones, we see this balling of the mercury together. It's adopting a spherical shape on the top. Water, we can also compare its cohesive forces and its adhesive forces. And it turns out for water, the adhesive forces are greater. This gives the shape you might be familiar with in a meniscus, pointed upwards with water, because again, it's this relative tension between the adhesive forces and the cohesive forces. And with water, the adhesive forces are greater. Capillary action is a phenomena that makes use of both of these. Both of these meaning the attractive forces that are between the liquid and the glass wall of the container, and then also the bringing together of the liquid in a spherical shape due to the surface tension. What you find is that the water begins to creep up the walls of the container, and then the capillary action causes it to ball together, and that draws it upwards. And then we have the creeping again up the sides, and then balling together, pulling it upwards. It doesn't continue indefinitely. Eventually, the force of gravity counteracts that. But that's been shown here how liquid can go up the membranes within a piece of celery due to capillary action. Let me show you a demonstration of this, another discussion. I'm curious if you've ever tried an experiment like this. And within this video, why do you think the diameter of the capillary tube is important?
Have you seen a paper towel soaking up water which was spilled? Do you know how this happens? The paper towel has narrow pores which absorb water by capillary action. To understand capillary action, let us undertake the following activity. For this, we need two capillary tubes of different diameters and a beaker of water. Take a half-filled beaker with colored water. We will use colored water here so that we can clearly see the water levels. Place the capillary tubes in the beaker vertically. See the water levels. The level of water in the capillary tubes is higher than the level of water in the beaker. The narrower the capillary tube, higher the water level. Why does this happen? All liquids have cohesive properties because of which all the molecules tend to stay together. This creates surface tension. Some liquids have adhesive tendencies by which they are attracted to substances unlike themselves. For example, water adheres to glass. Thus, in the experiment, as the water along the edges of the glass tube adheres to the glass, it rises along the sides, forming a small curve of water. The remaining water in the middle of the tube too rises up as a whole because of surface tension, which holds the water molecules together. These two phenomena together raise the level of water in the glass tube. The level to which the liquid rises is dependent on the diameter of the capillary tube. Capillary action is used in many modern fabrics to remove sweat from the surface of the skin. Did you know that water rises up the stem in trees by capillary action?
Within this video, we've looked at three properties of liquids: viscosity, surface tension, and capillary action. What questions do you still have about any of these?